Welcome to Week 1, Lab 1, the capstone of the week. This is part 1 of 5. Everything you read across chapters 1.3 through 1.5. Estimators, sampling distributions, the law of large numbers, the central limit theorem, and the machinery of a hypothesis test was about quantities you cannot see. A population mean, the spread of an estimator across hypothetical redraws of the universe, the true error rate of a decision rule. In a real study, you get one sample, and you must reason about the infinity of samples you did not get. In this part, we frame the whole lab and set up our tools. A simulation lets you cheat in the best possible way. You will build the universe yourself, fix its true parameter, and then draw from it as many times as you like. Because you know the true answer, you can check whether the tools actually do what the chapters claim. You will watch a sampling distribution tighten, like 1 over the square root of n, and go normal. You will write a 1 proportion test from scratch and then measure, not assume, its false positive rate and its power. And you will run a small p-hacking experiment that shows, in numbers, why a lone significant result pulled from many tries means almost nothing. The running object is the simplest random thing there is. A coin. Sam wants to know whether a coin or a trading signal that is right with some probability p, or a fair lending audit asking whether an approval rate is really 1/2 is fair. A coin flip is a Bernoulli trial, an experiment with 2 outcomes, 1 for heads with probability p, and 0 for tails with probability 1 minus p. The mean of a Bernoulli is exactly p, and its variance is p times 1 minus p. That clean known structure is what makes the coin the perfect teaching universe. Every quantity you estimate has a true value you can write down. Before you start, set up cleanly. Create and activate a conda environment, then install NumPy, SciPy, and Matplotlib. Then follow 2 rules of reproducibility without exception. First, pin the seed. Use NumPy's modern generator, RNG equals NumPy, default generator of a fixed seed, not the old global functions. A pinned seed means anyone who reruns your code gets your exact figures. Second, draw all randomness from that one generator. Do not mix in a second source. One honest caveat, Monte Carlo estimates are themselves random. When you measure a size and get 0.0487 instead of exactly 0.05, that gap is not a bug, it is sampling error in the measurement of the procedure. The fix is more reps. Reruns with the same seed will be identical. With a different seed, they will wobble. Summarize part 1. A simulation lets you build a universe where you already know the truth, then audit whether the statistical tools deliver what the chapters promised. The coin is the ideal universe, because a Bernoulli has mean p and variance p times 1 minus p. So every quantity you estimate has a known value to check against. Pin one seed and draw all of your randomness from that single generator, so every figure is reproducible. In part 2, we build the coin universe and watch the sampling distribution of the estimator form before our eyes.